So, in continuation of our earlier, the lecture on based on the photochemistry of carbon compound, we have mentioned that the photochemistry of carbon compounds undergo four different types of photochemistry. Carbon compounds undergo four different types of photoreaction. The Norrish type 1 and Norrish type 2. These two reactions are highly common in mostly in aliphatic hydrocarbons or alicyclic carbonyl compounds, alicyclic ketones, or open chain aliphatic carbonyl compounds. So we'll just see, we have already seen few examples of this. We'll see some more examples based on the noise type current. So aliphatic ketone, if we have examples of examples based on based on Norrish type 1 reaction. If we have a compound like this, CH3, tertiary butyl group, and then we have C double bond O, and then CH2, CH2, and CH3. So this, if we have a system, we have a carbonyl compound like this, and under photolytic condition, we know that this will undergo Norrish type 1 reaction. Will undergo Norrish type 1. Norrish type 1 reaction is nothing but is alpha bond cleavage. As far as this ketone is concerned, we have this is alpha bond, and this is also alpha bond. This is alpha carbon, and this is alpha also alpha carbon, and then both the bonds are alpha bonds, and this, since the two alpha carbons are unsymmetrically substituted, we have a CH2 here and then connected with ethyl group, whereas this alpha carbon is connected with tertiary bond. So as far as when we have a ketone like this under photolytic condition, we have to see that which cleavage is going to give more stable carbon center radical. If we cleave this, we end up with the acyl radical CH3 CH3 plus CH2 and CH3. So this is a primary radical, and if we cleave this, we end up with a tertiary butyl radical CH3 this radical plus acyl radical. So there is a competition between the alpha bond cleavage, and as far as the acyl radical is concerned, this is substituted with this. So now this is a tertiary radical, and which is more stable than the primary radical. So is going to be a preferential. This will not cleave like this. This will go preferential alpha bond cleavage under photolytic condition. Go preferential alpha bond cleavage to give this tertiary butyl radical as well as this acyl radical. We know that the acyl radical undergo very efficient decarbonylation. We lose CO to give you a give CH2 and carbon center primary carbon center radical, and then as far as the products are concerned, we get a coupling of this radical, we get a coupling of this, and then coupling of both the radicals. So if we get this will get dimerized to give CH3 ditertiary butyl group. So this is one of the product. If we dimerize this, we end up with the CH2, CH3, and then say CH3, CH3. So these two CH2 from one, so 3 carbon from another carbon. So you get, and then if we combine these two radicals, then we end up with the CH3, CH2, CH2 and CH3 and tertiary butyl group. So these are the products which are formed through the alpha bond cleavage of this. So photochemistry of this particular ketone, in the presence of this ketone in the presence of light undergo Norrish type 1 reaction. Norrish type 1 reaction is nothing but is alpha bond cleavage, and when there is these alpha carbons are unsymmetrically substituted, then we should look for which alpha bond cleavage is going to give more stable carbon center radical. So we are going to get a tertiary butyl radical here, and this cleavage is going to give you a propyl radical here. This is a primary radical. Tertiary butyl radical is more stable as compared to primary, and hence this ketone in the presence of light undergo preferential alpha bond cleavage, which is a type 1 reaction to give you these two radicals. There is acyl radical as well as tertiary butyl radical. This will undergo very fast decarbonylation to give this radical, and then this will undergo radical coupling to give three alkanes. So higher alkanes are formed. This coupling of these two radicals as well as dimerization of, so 1 and 2 are dimerization of these carbon center radical, and third is the coupling of both the radical which form after the alpha bond cleavage and Norrish and the decarbonylation reaction. So we go further and look for another example. Say for example, now what is the evidence that the Norrish type 1 reaction, I mean these ketones in the presence of light undergo alpha bond cleavage to give either this radical or this radical. So in order to prove the first step involved in the aliphatic ketones in the presence of light is the alpha bond cleavage to give acyl radical as well as carbon center radical was established by trapping of these carbon center radical as well as acyl radical by trapping agents. And here is an example where it very clearly shows that aliphatic ketones undergo. So if we have a ketone like this, C6H5 CH2 C double bond O CH2 C6H5, this is a dibenzyl ketone. This in the presence of light. Of course, this is symmetrical. Whether if we cleave this or we cleave this, we end up with the same stability carbon center radical. So we in the presence of, this is a type 1 reaction. This will undergo type 1 reaction in the presence of light. Type 1 reaction is nothing but is a alpha bond cleavage to give C6H5 CH2 radical plus C double bond O CH2 C6H5. So we get these two radicals. Now the cleavage, alpha bond cleavage of this ketone to give these two radicals was well established by trapping of tetramethyl N oxide, which is a very good trapping agent. So it was when it was treated with tetramethyl NN tetramethyl piperidine N oxide radical, tetramethyl piperidine N oxide radical, tetramethyl piperidine N oxide. So this is a very good trapping agent, and when this was treated with these and it has been found that the products obtained was C6H5 CH2 O plus C double bond O, O, CH2, C6H5. So the formation of these N oxide, I mean these products very clearly establish that the Norrish type 1, the photochemistry of aliphatic ketones like undergo Norrish type 1 reaction, which is alpha bond cleavage to give you acyl radical and the carbon center radical. The reaction which in turn reacts with radical trapping agents such as this tetramethyl piperidine N oxide to give this two products. So this product has been well established, and the formation of these products very clearly indicate that the first step involved in the Norrish type 1 reaction is alpha bond cleavage, which gives this acyl radical and carbon center radical, which further undergo decarbonylation and radical coupling and so on and so forth. So this is well established beyond doubt that the reaction proceeds in this fashion to give this. So if we have so let us see the more examples. If we have if we have a starting ketone like this, CH, C double bond O, CH, PH. So this if we have a ketone like this, what is the what type of photochemistry this will undergo? We know that this is, of course, is a ketone, and then it's connected with this CH diphenyl pane, and then this will definitely undergo type 1 reaction, which is alpha bond cleavage. So we can, since this is symmetrically, either we cleave this bond or we cleave this bond, we end up with the similar stability carbon center radical. So we just cleave this to get PH, CH, PH, C double bond O plus CH, P. So this is the first step in the photochemistry of this ketone to give you acyl radical and carbon center radical, and this has been known to undergo, acyl radical has been known to undergo very fast decarbonylation. This will undergo the minus loss of CO to give pH, CH, pH radical, and then of course this will couple, the radical coupling is going to give CH, CHPH. So this is one of the most probable products which is formed during the photochemistry of this ketone, and it has been well established the product. So these are the few more examples in continuation with the Norrish type 1 reaction. Aliphatic ketones undergo Norrish type 1 reaction to give you acyl radical and carbon center radical. If the alpha carbons are substituted or unsymmetrically substituted, then we should go for which cleavage is going to give you more stable carbon center radical. So that alpha bond cleavage is going to preferred, and then followed by decarbonylation, and then followed by radical coupling. So and the cleavage of alpha bond cleavage to give acyl radical and carbon center radical is well established by trapping of radical trapping reagents such as this particular tetramethyl piperidine N oxide, and the formation of these two radical trap products indicates that the initial step involved is these reactions. This is another example. Just see the possible photoproduct formed during the Norrish type 1 reaction of this diphenyl substituted ketone. Now going further and then see if we have a system, the photochemistry of cyclic ketones. Photochemistry of cyclic ketones have already been discussed, and few examples have been looked. We will look few more examples. If we have a CH2, CH2N, CH2, and then C double bond. This is cyclic ketone. N could be 1, 2, 3, and depending upon, then we have a if it is just 1, then or 2, so 2, 3, 4. We can have a cyclobutanone. We can have a cyclopentanone. We can have a cyclohexanone, and so on and so forth. Depending upon N is equal to, can have 1, 2, can have 2 here, and 2, 4, can have 2, 3, 4, and so on and so forth. So we can, and then this is a alicyclic ketone under photolytic condition, and this also undergo type 1 reaction. Very prominent photoreaction is a type 1 reaction in these cyclic ketones, alicyclic ketones, which is nothing but alpha bond cleavage, and then so these also alpha bond, these also alpha bond. This is symmetrically substituted. You have a CH2, so we can with a cleave any of these alpha bond, so we can have a CH2N, depending upon how long is the chain, CH2 C double bond O. So you have a this is the first step in a cyclic ketone, where we have an acyl radical and carbon-centered radical. Now this will is the different pathways are open for this. This will undergo decarbonylation, CO, to give CH2N, and then CH2, this radical, and then this will combine to give CH2, combined with CH2, then CH2N. So this is one of the product with the cycloalkane with the loss of carbonyl compound. Other possibility is the abstraction of an hydrogen. This will abstract this acyl radical will abstract a hydrogen atom from the adjacent CH2 groups, and then this will form a cyclic ketone. So this is one of the product which is formed. So we can get when this abstract from the hydrogen atom, this will become double bond, and this will become aldehyde. So this so we'll just put say one more CH2, and then we get CH2. So is going to abstract a hydrogen atom from here, then it will form an aldehyde. This will get CH2N, and then this will form a double bond here. So CH double bond CH2. In aldehyde is one of the product, and then this will also abstract a hydrogen atom from here. This gives ketene. So this is going to abstract a hydrogen atom from here to give CH3, CH2, of course, N here, and then this will become C double bond O or C double. This is a ketene derivative, and then ketene will, in the presence of solvent, say alcoholic solvent, give an ester, CH3, CH2N, and then we get C double bond O, OET, OR. So get an ester. So this is one another product which is formed. Is also quite possible that this radical. So these are the few products. One is the decarbonylation, is the aldehyde, and then this will also lead to a, a an abstraction of this radical about this is a ketene derivative. So you can, so these are the few products which are possible in the case of cyclic ketone. And let us see a few more examples just to have a better understanding. If we have a cyclohexanone, if we have a cyclohexanone, this is a general reaction where n can vary. So if we just take a few particular cyclic ketones, say for example, we have this one in the presence of H light, so this will undergo type 1 reaction. Type 1 reaction is nothing but is a alpha bond cleavage. Is going to, we can cleave any of these because both the alpha carbons are symmetrically substituted. So whether we cleave this or we cleave this is not going to make any difference. But if the alpha carbon is substituted, then we will look for more stable carbon center radical, because in either way the acyl radical stability remains the same. So if we cleave this, we end up with a, this is the first step. Acyl radical, first step, acyl radical and carbon center radical. There are different pathways open for this. Number one is the minus CO decarbonylation to give a and then this will combine to give a 5-membered ring. A 6-membered ring is going to end up with a cyclic carbocyclic system with the exclusion of carbonyl and 1 carbon CO exclusion to give a cyclic system. Is another path which is open here is the abstraction of a hydrogen atom by this acyl radical. Then this become aldehyde and then this will become an ene. So we end up this is an aldehyde, and it is also possible that this radical will abstract a hydrogen atom from here, then it becomes ketene. So this becomes CH3 and then this become ketene, and then ketene in the presence of solvent, say for example if we have an alcoholic solvent, we get an ester, and if you have a small amount of moisture, we give it an acid, corresponding acid. So corresponding ester will be C double bond O, OR, and then this is CH3 of course, and the corresponding acid will be CH3 okay 1 2. So I think this is, there should be one more carbon here. So we have this one, OR. Okay, so these are the possible product which are which is there is also possible that this will there is a possibility of a open chain E, and so if this will abstract an hydrogen atom from here, then it may lead to this particular ene. So you have a one carbocyclic system, an open chain ene system, an aldehyde system, is an ester or an acid depending upon the so this is mean is a ketene intermediate, and so on and so forth. So these are few possible products which are which may take place if we have a alicyclic ketone. So another we'll see a few more example. Say for example is this one. This is also in principle under photolytic condition. If we shine light, in principle undergo type 1 reaction which involves alpha bond cleavage. Now here you see this alpha carbon, this alpha carbon. Now this is going to give, if we cleave this, we are going to give this radical, and then this radical. If we cleave this, we end up with now. If we look at the stability of now, as far as the stability of acyl radical is concerned, in both the cases is more or less same, but this stability, carbon center radical, is going to decide. This is a of course there is an H here. This is a secondary radical, and this is a primary radical. We know that the order of stability of radical lies in the order tertiary is more stable. Tertiary is more stable than secondary, more stable than primary, is more stable than methyl radical. So according to this order, this is more stable, and this is less stable, and hence this is going to form, and this is not. So when the alpha carbon is substituted, then there will be a preferential alpha bond cleavage. Alpha bond cleavage preferential alpha bond cleavage takes place, and then this will undergo different reaction. Number one, minus CO to give this radical, and then this will combine to give carbocyclic system. This will abstract in hydrogen atom from here to give an aldehyde H. So rest of the reaction is going to be same. This will abstract even it can abstract a hydrogen atom from here to give a double bond here. It may also give an aldehyde here. This may abstract, this will abstract here to give a ketene intermediate. And then this will, in the presence of solvent like alcohol, is give an ester, and then if it is a small moisture water, then it is going to give an acid. So these are a few possible photoreactions which may take place during the photolysis of a alicyclic ketone, as well as during the photolysis of a open chain carbonyl compounds. So the most prominent reaction of the ketones are mostly in alicyclic ketone. The alpha bond cleavage is nothing but is a Norrish type 1 reaction. Alpha bond cleavage is preferential. If alpha carbon is substituted and is going to give the different stability carbon center radical. So more stable carbon center radical is going to be preferred, and which will further undergo decarbonylation, radical coupling, and so on and so forth.